Yes, Sanjeev, my screen is visible.
Yes, sir, it's visible, sir.
Okay, thank you so much.
Okay, sir.
Yeah. So, good evening, students. So, today we have 14th class and unit number 3. So, we are today ending the third unit, that is a battery energy storage system. So, in the previous class, we discussed the operational characteristic of proton exchange membrane fuel cell for e-mobility and then mathematical modeling of proton exchange membrane fuel cell. Is there any confusion, any query from the previous class? Because in the last class, nobody asked any question. I got only one question, and at that time, I was given the answer. And question was, uh, efficiency of the fuel cell, that is only for 50 to 60% of the hydrogen cell. Still people are use the hydrogen vehicle. Why? So that time I already given the answer. So still, if anybody have any query from the last lecture, then please let me know. Otherwise we can start the new topic. Is there any query, any confusion from the previous class? Okay, so today we are going to end with the third unit. So today we will complete the third unit, and that one is last topic is size of the fuel cell plant. So what is the size of the fuel cell plant? Balance of the plant. So we need to operate the balance plant and how we can do it, and hydrogen storage system, and supercapacitor for transportation applications. So these four topics we will discuss in the today's class. So sizing of the fuel cell plant. So how we can decide the size of the fuel cell plant, correct? So what are the major parameters we have to consider for the size of the fuel cell plant? So multiple fuel cell are typically arranged in the series as a stack. So in the battery, we can say it is a battery pack. Similarly, in the fuel cell, we can say fuel cell in the series as well as a parallel combination. So you can think it is the same like the battery pack, correct? Here is a energy density is a different because hydrogen energy density is different and the battery energy density is different. But state connection it is the same, series and parallel combination of the same. In order to achieve the voltage and power level required for the automotive powertrain. So maybe the power level is maybe the 1 kilowatt, maybe the 500 watts. So depend on the power requirement, we have to connect the series and parallel combination of the cells, correct? And we can say it is a fuel cells. The fuel cell stack voltage should be higher as possible in order to maximize the overall efficiency, correct? So uh, it, it is required to get the maximum efficiency of the maximum voltage of the fuel cell, so we can get the maximum efficiency of the electric power train. Okay, so we are trying to take the maximum voltage of the one cell. Hundreds of the individual cell are typically required in the series, so we will get the more voltage level, correct? So all of you know about the, suppose we can connect the series of the battery, then we will get the addition of the voltage. Suppose you have a one cell voltage, maybe the 5 volt, and this 5 cell you can connect in the series, so you will get the 25 volt, correct? And suppose you want to increase the current level, because current is depend on the load, but still we can say it is a parallel connection. Suppose you want to increase the current capacity, then we have to connect each cell in the parallel combination, because in the parallel voltage will be same. The current and power of the fuel cell are proportional to the area of the fuel cell. Yes, so we can say it is a meter square. Okay, so maybe this is the fuel cell, one fuel cell, correct? So maybe this is the 1 meter and this is the 1 meter. So we can say area is a 1 meter square. Okay, so that is a depend on the power rating. So that is a directly proportional to the area. Thus, the area of the individual fuel cell is sized in order to output required power. Okay, so that is a totally depend on the area, how much area is required. So you will get the required power level. So how we can find out? So mathematical equation. So if possible, then you can note down. So because based on this formula, we will do the numerical. The stake output voltage from the fuel cell power plant. So V subscript FCP, that is a fuel cell power plant, is given by number of fuel cell into the voltage of the fuel cell. So NFC, there is a number of the fuel cell in the fuel cell stack. So suppose we have a one stack. In one stack, maybe the 10 fuel cell, maybe the 20 fuel cell. So NFC, there is a number of fuel cell into VFC. What is the voltage level of the single fuel cell? Correct. So then we can find out the voltage capacity of the fuel cell power plant. The fuel cell power plant output power, there is a FCP, there is a fuel cell power plant, is determined by multiplying the fuel cell stack output power by the efficiency of the balance of the power, BOP. So fuel cell power plant is equal to efficiency of the balance of power plant, balance of the plant, into fuel cell output power, there is a PFC. So these both equations are most important for the numerical. The area, so how much area is required for particular the fuel cell? The area of the individual fuel cell AFC is simply the ratio of the maximum output power of the stack, there is a VFC, to the product of the number of cells and the maximum specific power, there is a PSFC. So S indicates the specific and FC, there is the fuel cell. So AFC, there is the area for the fuel cell is equal to ratio of the power of the fuel cell divided by NFC, there is a number of fuel cell, into power of the specific fuel cell. So that based on this formula, we can decide the area of the fuel cell. If the thickness of the fuel cell, that is a TFC, TFC is nothing but thickness of the fuel cell, is known, then volume of the fuel cell, VFC, is given by VFC is equal to number of fuel cell, thickness of fuel cell, and area of the fuel cell. Maybe the thickness of fuel cell, maybe the 1 mm, maybe the 2 mm, maybe the 3 mm. So we can design the thickness of the fuel cell. There is up to there is a vary by company to company, correct? But we can try to make the like nominal thickness, maybe the 2 mm, maybe the 3 mm. Okay. The energy input of the fuel cell, E input. So what is the energy input of the fuel cell? So energy input of fuel cell, there is a ratio of the FCP divided by efficiency of the FCP into the T, and T is a number of T is a time. Okay. So that is the energy input of the fuel cell. So fuel mass flow rate of the hydrogen, correct? So fuel mass flow rate of the hydrogen, there is a MH2, because we can flow the hydrogen from the anode, correct? So first we have to go through the anode, then there is a chemical reaction with the cathode, and we can generate the energy, correct? So MH2, there is a flow, mass flow of the hydrogen is equal to energy input divided by Q into T. So again, we can simplify, otherwise we can put the value of the E in this formula. So we can say, so we can put the E in value in this equation. So we can simplify this equation, and final equation value, there is a PFCP divided by efficiency of the fuel cell into the Q. Well, Q is nothing but megajoule constant, it's a 33.33 kilowatt hour. Otherwise, 120 megajoule per kilogram is the specific energy, otherwise the lower heating value of the hydrogen. So Q is a constant, and that indicates the lower heating value, and value is 33.33 kilowatt hours. Yes, till now any confusion? So till now we discussed the total six formula. So based on this we can do the numerical. Yes.
Sir,
Yes.
But the output of fuel cell is very small. Then how can we increase the cell voltage? Just like in lithium ion batteries and other batteries cells, the cell for voltage is large. They generally 3.7 or 4.2 at full charge voltage, and the voltage of individual cell in fuel cell is very small. So how can increase it?
Yeah, so we have to connect the DC to DC converter. So for one fuel cell, voltage is a very less. Maybe the 1.2, yeah, maybe the 1.3, yeah, maybe the maximum is a 2 volt, correct, per fuel cell. So we have to connect the series of the series of the cell, and then we can make the one fuel stack. After that, we have to connect the DC to DC converters. By DC to DC converter, we can increase the overall voltage. Correct. Otherwise, we cannot increase the per single fuel cell voltage, because till now we don't have any technology, so we can increase the maybe the single fuel cell voltage, maybe the 10 volt, yeah, maybe the 20 volt. It's not like that, because till now we don't have any technology, so we can increase the per cell voltage. It is not like that.
Then we have to, sir, we have to connect many cells in series, sir.
Yes, so
So,
maybe we have to connect like maybe the 1000 cell in the series, yeah, maybe the 1500 cell in the series. So that depend on the power requirement.
and then what would be the size of the sir plant and cell?
There is a very big size. So normally, what happen in the electric fuel cell vehicle? So they are using the fuel cell as well as the battery both. So initially they use the battery to starting, because during the starting they require the more torque, more power, correct? So initially they take the voltage, otherwise initially they take the energy from the battery, and during the running condition they can change the from battery to the fuel cell. So I will show you the one example. So there is a Mirai car in today's class. So what is the size of the battery? What is the size of the fuel cell? I will show you in this lecture.
Sir. Okay, sir.
Okay. Yeah. So now we can do the numerical. There is a size of the fuel cell plant, correct? So based on those formulas, so till now we discussed the total 6 formula. So based on those formula, we can do one example. So you will get the idea. So how we can decide the fuel cell size and other parameter. So first numerical, fuel cell power plant output is a 114 kilowatt. So you can see the fuel cell power plant output is a 114 kilowatt and has 370 cells in series. The parameters of the fuel cell are provided in the table 1. The cell thickness, that is a TFC, is the 1.34 mm. So these are the parameters, as well as this are also parameter. So now we have to determine the area of the each fuel cell. So we have to determine the area of the each fuel cell, volume of the stack. So what is the volume of the stack? Mass flow rate of the fuel. Also we have to find out the mass flow rate of the fuel, and stack voltage at full power for the full load condition of 50,000 ampere per meter square. So we have to find out the first parameter, there is the area of the each fuel cell, volume of the fuel cell or volume of the stack, mass flow rate of the fuel stack, and stack voltage. And finally, fourth one, that is a stack voltage. So in the yesterday class, we already discussed this parameter. There is a Gibbs energy density. So this Gibbs energy, free energy. So same parameter yesterday we use for one of the example, correct? Faraday constant, fuel cell area, specific resistance. So one by one we can calculate the parameter, correct? Yeah. So first one, that is a fuel cell, uh, area of the fuel cell, correct? So we can find out the one by one. So fuel cell power must the factor of the balance of the plant, correct? So first we can find out the solution. So PFC is equal to PFC is that is a given 114. So there is a fuel cell power plant output 114 kW. So we can say 114 divided by efficiency, that is a 0.8, correct? So in the previous example, in the yesterday class, we take the same parameter. So there is, we can say there is a efficiency is a 0.8. So in this example, I missed the efficiency. So, but there is a value is a 0.8, correct? In the yesterday class, we already discussed that is the same numerical and same parameter we are considering here. So that's why there is a 0.8. Okay. So PFC, that is a fuel cell power, there is a 142.5 kilowatt. So I will add this one, that NBOP, there is a balance of the power efficiency, there is a 0.8. Okay, there is a missing in the numerical, I will add. Okay, so there is a fuel cell power. Now we have to calculate the area, because our main task is the area. Area of the fuel cell. Fuel cell stack is AFC is equal to PFC divided by NFC into PSFC. So we already calculate the PFC, there is a 142.5 kilowatt divided by NFC. NFC is given, yes, 370. NFC is given, there is a number of fuel cell 370 into specific energy, there is a 9315. So that is a specific energy is given. Your specific energy is also missing. PFC value is a 9315. PSFC is equal to 9315. Okay, so there is a specific power 9315 watt. Okay, so what is the answer? So what is the area? Yes, anybody? What is the area? So this is the kW. Okay, so what is the area? AFC. For my calculation, 142.5 kW, 370 into 9315 watt. So that is around like 0.0413. That is a meter square. So this is the area of the single fuel cell, 0.0413 meter square. Okay, so this is the area for the fuel cell stack. There is a 0.0413 meter square. Now we have to find out the volume. Volume of the fuel cell. So volume of the fuel cell. Volume of the fuel cell, there is nothing but number of fuel cell into thickness of the fuel cell into area of the fuel cell. Number of cell, there is a 370. Thickness of the fuel cell is given. Yes, 1.34 mm. 1.34 mm, that is the thickness is given 1.34 mm. AFC we already calculated 0.0413. 0.0413. So volume of the fuel cell 0.0205 meter cube. So this is the volume of the fuel cell, and the mass flow rate of the hydrogen mass flow rate of hydrogen. So formula is the PF Cp divided by. So formula is most important. Huh? So please remember the formula of the all the size of the fuel cell.
Sir, so
Yes,
1.34 is in mm. Then
1
another
point.
1.34 is in mm. Then how can meter cube?
So volume, correct?
1.34 mm in written there and 0.025 meter cube here.
Just 1 minute. Just 1 minute. So here is a meter square. Thickness is a meter square. So because thickness we can measure, that is like, so this is suppose is fuel cell. I already explained this one here. Yeah. So thickness is like this. So 1 mm and 1 mm. So we can say 1 mm square, correct? So that's why. So this is the mm square. So TFC there is a mm square, and then another one is your uh, this one, this area. So that's why maybe the unit balance area is this one is a mm square.
mm is converted into meter, sir.
Just 1 meter.
Yes, sir.
Area is just 1 meter.
Area is in meter square.
Area is a meter square, correct? And meter is converted into mm, correct?
Mm is converted into meter, sir.
Just one, just one. Area is in meter. Just one. Yes, correct. So this one is correct. So this one is correct. So thickness is a 1.34 mm, and area is converted. Yes, you are correct. Yes. Got it?
Yes,
Now
sir.
it's yeah. Now got it. Yes. So there is yes unit balance. Yeah. So mass flow rate of the hydrogen. So there is a ratio of the fuel cell power plant divided by the efficiency of fuel cell plant into the Q. So Q is a constant, and that is your Q is nothing but lower heating value, and that is a 33.33 kilowatt hours. So we can put the all the value. So we can say the 114 kilowatt divided by efficiency, that is a 0.5325. 5325 into Q value, there is a 120. Yes. So 120 megajoule divided by kg. Otherwise, you can convert the 33.33 kilowatt. So we can say 33.33. So hydrogen mass flow rate of the hydrogen mass. So we can say it is a 1.78 gram per second. So you can convert in that kilowatt, and that is hour. So that's Q that is your we can say 33.33 kilowatt hours, correct? So we can convert the unit, and finally we can say mass of the flow of the hydrogen, that is a 1.78 gram per second. Okay, so that is a conversion. So if any missing, then please let me know. Huh? So in the previous example, in the previous class, you said so there is a meters cube, correct? So please let me know if any mistake. So this is the mass flow of the hydrogen. Now, stake voltage, there is the last one. Stake voltage is, so stake voltage we can define VFC equal to NFC into VFC. So NFC there is a 370 and VFC there is a 0.621. Correct? So VFC there is a 0.621. So finally, stake voltage there is a VFCP is equal to 230 watt. Correct? So is there any confusion for this numerical? So we have a certain parameter of the fuel cell, and as well as the detailed parameter of the current density and every parameter. So we have to find out the fuel cell area of the each fuel cell, volume of the stake, and mass flow rate of the hydrogen, and stake voltage at the full load condition. Is there any confusion, any query for this numerical? Because numerical is most important for this subject as well as the for understanding. Okay. Now next numerical. So this one is detailed example. So I considered the like practical case. So there is a tractor. So in this example, a fuel cell system is sized for the tractor. So normally we use the tractor in the agriculture field. Tell the carry the goods from shipping port. Correct. So tractor is used for carry the luggage. Otherwise, we can say carry the goods. The maximum gross weight for the tractor Taylor combination is 36280 kilogram, 36,280 kilograms. And vehicle operates at an average speed of 64 kilometer per hour. So there is operating speed is 64 kilometer per hour. The vehicle has following parameters. So a lot of parameters is given. So gross weight, vehicle weight, that is M 36,280 kilogram when fully loaded, or 1360 kilogram when unloaded. Correct. So you can consider. So only tractor weight there is a 13,600 kilogram, and with loaded there is a 36,280 kilogram. Drag coefficient, there is a CD. So in the first unit, we already discussed drag coefficient, there is a 0.7. Vehicle cross-section area, there is a 10 meter square. And coefficient of the rolling register, CR, there is a 0.008. So nominal efficiency of the powertrain and transmission, there is a eta PT, there is a power efficiency, there is 85. And auxiliary load, there is a P is equal to 2 kilowatt. Correct. Let the density of the air, so air density, that is your 1.2 kilogram into meter cube. Correct. So we can say kilogram per meter cube. So we can write kilogram per meter cube. Okay. So these are the parameter. So what we have to find out? Overall mass of the fuel cell system, including the fuel cell, balance of the plant, storage tank, mechanical bracketing, is 400 kilogram plus 80 kilogram per 5 kilogram of the stored hydrogen. Okay, so 40 kilogram, 400 kilogram plus 80 kilograms per 5 kilogram store of the hydrogen. So these are the tank capacity we can say. So our role is we have to find out these two things. First thing, we have to determine the miles per gallon equivalent. Okay, miles per gallon equivalent. So we have to find out because we are using the hydrogens and we can measure in the gallon capacity. Otherwise, the kilogram, correct? So we have to find out the miles per gallon equivalent and overall mass of the fuel cell if the vehicle is travel a constant speed 64 kilometer per hour. So suppose vehicle is running and travel for the constant speed 64 kilometer per hour. For the full load work shift of 8 hours or the 512 kilometers. The fuel cell plant efficiency is 48% for this operation. Okay, so first one we have to find out the mile per gallon equivalent. Second thing, we have to find out the mass of the battery which will be required if the battery pack specific energy is a 0.15 kilowatt hour per kilogram. So we have to find out the battery capacity, correct? And finally, we have to give the conclusion. Otherwise, finally, we have to give the statement. What are the challenges facing the battery for this application? As I said in the beginning of the lecture, we are using the battery, correct? So initially, we are use the battery to start our vehicle. Once our vehicle is running, then we can switch over into the hydrogen fuel cell, correct? So we have to give the justification. So what are the challenges facing the battery for this application? Correct? Got it? So we have to calculate only two parameters. First one is a mileage per equivalent, and second one we have to find out the mass of the battery. Okay. So lengthy numerical, but this is a practical case. So I already solved this numerical. So let's see one by one we can do it. So first we can find out the velocity. So please remind, otherwise please revise your concept. So there is a first unit. So we have to find out the velocity. Velocity V. So V is nothing but your 64 divided by 3.6. Okay. So 64 divided by your 3.6. So this is your velocity. So velocity is how much? So there is here 70.78 meter per second. Because we have to use velocity in some way. So we will use the velocity value. Now the load power, the road load power of the fully loaded vehicle is PV equal to 1 by into rho into CD into area into VQ plus CR into M into G into V. So please remind your concept. So maybe you will get this formula, correct? So we have to put all the value 1 by 2, raw value is given, there is a 1.2, CD is also given, there is a 0.7, area is also given, there is a 10, velocity we already calculated 70.78 cube, and CR is also given, there is a 0.08, mass is given 36280 into gravitation, there is a 9.8, velocity there is a 70.78. So PV is equal to 74.78 0.23 kilowatt. Please cross verify. Huh? So that is the on-road power, correct? So on-road power of the vehicle, there is a 74.23 kilowatt. So please cross verify mathematical calculation. Maybe the sometime I did mistake.
Sir,
Yes.
this type of power, is it a combination of drag force plus rolling resistance force, sir?
Mm-hmm.
The total power represented by a combination of a drag force as well as rolling resistance. Is it correct, sir?
Yes. So that's why I added both now.
I think it's combination of both.
So
Yes,
that's why
sir.
I added. So this is your rolling register, and this one is your drag force.
Okay, sir.
There is a both combination. So CD, it is a represent, there is a drag force, correct? So drag coefficient CD, and CR, there is a rolling register coefficient. So there is a both one. So total power is both, correct? Okay. Yes. Next, the fuel cell plant output power. To the powertrain plus the auxiliary power. Okay, so plus auxiliary power. So we can define P S FCP is equal to PV divided by eta PT plus P auxiliary. So what is a PV? So 74 point somewhere is defined 74.23. Uh, 74.23. Just 1 minute. PV we calculated, yeah, what?
Yes, sir. Calculated, sir.
Yes, PV we 74.23, correct? Yeah, 74.23 PV we calculate 74.23. Yes, in previous one 74.23 kilowatt divided by NPT. So NPT is a 0.85 efficiency plus auxiliary power. Auxiliary power is given, I think so.
2 kilowatt maybe, sir.
Auxiliary power 2 kilowatt, correct? Yes, here 2 kilowatt. Auxiliary power is given 2 kilowatt. 2 kilowatt. So how much? PFCP. So as per my calculation, there is 89.33 kilowatt. Is it correct? Please cross verify. 89.33 kilowatt. Correct? Yes. Now the overall, because for the 8 hours, correct? The overall driving time is 8 hours. And so energy output by the fuel plant, and so energy output by the fuel cell plant is energy fuel cell plant is equal to PFCP into T. So PFCP 89.33 into T, that is your 8, correct? So there is a time 8. So EFCP is equal to 89.833 into 8. So there is a 714.6 kilowatt hour. So overall, this is a driving efficiency. Overall driving time is 8 hours. So that time energy output of the fuel cell plant, that is your 714.6 kilowatt hour. Okay. Now next one, we have to calculate the input energy carried by hydrogen fuel cell. The input energy carried by hydrogen fuel is hydrogen fuel is, so E in input energy is equal to ratio of the fuel cell plant energy divided by efficiency of the fuel cell plant. So 714.6 divided by efficiency of fuel cell 0.48 is equal to 1489 kilowatt hours. So this is the energy input. The mass of the hydrogen required, is mH2 is equal to E in divided by Q. So E in we already calculated, there is a 1489 divided by Q. Q is nothing but 33.33 because there is a constant. So mass of the hydrogen, that is a 44.67 kilogram. Okay. So this is the mass of the hydrogen, that is a 44.67 kilogram. Now, last one, for the first question, we have to finally define the MPGA. Yes, Amrita. Mile per gallon equivalent. Yes.
Unit is correct, sir, or mass rate will be represent, sir?
Here is asking the mass of the hydrogen. So there is a mass is the kilogram. So as per your knowledge, may be wrong.
In previous example, the unit of were used gram per second, sir. So I think
maybe you
the
can convert
mass
it.
Mass flow rate, maybe, sir.
Yeah, there is a mass flow rate, correct? So that's also per second how much mass flow rate. That's why, correct? In the previous in this example, correct?
Yes, sir.
So this is the mass flow rate. So that's why we converted into the gram per second. And here they are asking mass of the hydrogen. Okay, so that's why there is a kilogram. Okay, got it. Finally, we have to find out the mileage per gallon. Okay, so finally we have to, for first example, for first part, we have to find out the MPGE. MPGE, that is your mass, sorry, miles per gallon equivalent. Miles per gallon equivalent. MPGE. So MPGE is nothing but, so this is the new formula for you. So please remember this one. I will send you the derivation. So derivation, I will try to find out the derivation, but formula is MPGE S divided by 1.609 E in into GAL divided by 33.705. So 33.705 is nothing but your Q, correct? So Q value. So S value for this numerical is a 512106. E in we calculated 1489 into GAL. So GL is constant, as it is we can put into 3.30705. So this is the kilowatt hour. This is the kilowatt hour. Energy is also kilowatt hour. So this is also kilowatt hour. And 512, this is your miles. Okay, so this one is miles. So finally, MPGE is equal to so this MPG formula I did not derive in the previous class as well as this class, correct? So please remember this formula. So MPGE is equal to 7.2 mile per gallon equivalent. Sorry, MPG is equal to 7.2. So there is a miles per gallon, correct? So final unit, there is a miles per gallon. We can write the miles per gallon. Okay. Yeah. So first part we completed. So first we calculate the velocity, then we calculate the load power, then we calculate the fuel cell plant output, and finally we calculate the overall driving time, and then we calculate the energy input and mass of the hydrogen, and then finally we calculate the mile per gallon equivalent. Okay, so this mile per gallon equivalent formula, please remember. So commits, so commits we have to give. There is a significant challenges for the battery. So battery part is remaining, correct? So just I will add the one more slide. So we will calculate the second part also. Yeah. So now second part, there is a overall weight of the fuel cell system. So there is a second part of this numerical. So we have to find out the two things. So this is the first part we calculated. Now we have to calculate second part. That is a battery capacity, correct? So second part, the overall weight of the fuel cell system. So there is a mass of the fuel cell plant. So there is a 400 kilogram plus 80 divided by 5 mass into hydrogen. Correct. So this is the formula. So we can say the 400 kilogram, because that 400 is given, yes, 400. So you can see this is the 400 kilogram plus 880 kg per 5 kilogram hydrogen. So that's why 400 plus 80 divided by 5, that is 5 kilogram. Okay. So we can say 400 plus 80 divided by 5, and mass of the hydrogen, there is a mass. What is the mass of the hydrogen? There is a 44.67 kilogram. So into 44.67 kilogram. So this is the nothing but 115 kilogram. Okay. And equivalent final thing is a equivalent battery power. The equivalent battery output energy must equal fuel cell output energy. So equivalent battery output energy must equal to the fuel cell output energy. So it means we have to manage the both balance condition. Otherwise, there is a issue with the system. Correct? Suppose both are the like unbalanced, then maybe there is a issue with the system. First, the battery mass, hence the battery mass MB is, so finally we have to calculate the MB, correct? So MB is nothing but EFCP divided by SEB. So EFC we calculated, that is 701.6, and SEB, that is a given SEB, that is a 0.15 kWh per kilogram. So SEB, that is a 0.15. Okay. So this is the, like this one is a kilogram. So ultimately mass of the battery, there is a 4764 kilogram. So this is your final answer for the second numerical, second part, and this is the final answer for the first part. Correct. So this is a very big example, but it is a real practical application base. Now last part of this example, what are the challenges facing a battery for this application? So challenges is, you can see the mass of the battery. So this is a mass of the battery, that is a 7464. That is around like 500 kilogram. So we have to give the commits. So there are the significant challenges for the battery to compete with the fuel cell in the application. So these, first, the weight of the battery can be extensively for this tractor axial. Correct? So too much weight. Second, the vehicle can be rapidly refueled in the minutes using the hydrogen, while the time for the battery charging is likely to be significant and result in proportionate drop of the operating hours for the vehicle. Yes, so suppose you want to use the battery for this application. So size of the battery there is around like 500 kilogram, and it will take too much time to charge your battery. Suppose you want to use the fuel cell. So yes, we can use the fuel cell, and advantages is it will take only few minutes to recharge, refuel your hydrogen, correct? So it will take only 1 to 2 minutes. It is the same like the petrol and diesel. So these are the comments we have to give. Okay, so this is a very big numerical and but practical cases. Yes, any confusion, any query for this numerical? Only thing is you have to remember the one formula, that is your MPEG, mile per I forgot MPEG, mile per gallon equivalent, mile per gallon equivalent. Okay, so you have to remember this formula also. Yeah, any confusion for this numerical? Okay, now balance of the balance of the plant. So power plant is a general required significant support component and axially equipment in order to output power. So main component for the automatic fuel cell and balance plant. So this is the figure 1. So you can see this is the typically fuel cell. It is a look like this. This is a fuel cell, electric control system, cell stack assembly. So you can see the many cells are connected in series and parallel, and then finally it is a cell stack. Air processing system, because we can produce the hydrogen, we can generate the energy by the processing of the hydrogen and the oxygen, correct? So there is an air processing system, fuel processing system, and thermal management system. So these are the major components for the balance of the plant. Otherwise we can say the fuels, typically fuel cell system. Okay, so there are the server function for the fuel cell balance plant. First one is a fuel processing. So how much fuel processing we have to do? Air processing, how much rate of the flow of the air? Thermal and water management, because we have to use the cooling system. Electric controls, protection, DC to DC converter, because the fuel cell voltage level is down, so we have to use the DC to DC converter, so we can maintain the constant voltage, and we can also increase and vehicle level coolings. So these are the major components and function where we can use for the balance of the plant as well as the thermal fuel cell system. As discussed earlier, the energy requirement for the balanced plant can quite high. Yes, in the last 2 class we already discussed for the fuel cell energy requirement is high. Typically consuming about 20% of the fuel cell output power for high pressure fuel cell system, and about 10% of the low pressure fuel cell system to power required the fan, pump, and compressor, and so on. So normally there is a 20% and about 10% for the low pressure. For the high pressure there is a 20%, and for the low pressure there is a 10% for the required for the like auxiliary rod, maybe the fan, maybe the pump and compressor and everything, correct? So this is the practical example. So as I said, in India, Toyota Mirai is working based on the fuel cell. Otherwise, we can say the hydrogen vehicle. So there is a 2016, not the latest model, like 9 year back. So 2016 Toyota Mirai has 370 fuel cell in the single stack with cell thickness of 1.3 mm each. So 370 fuel cell connected in the single stack. The vehicle stores 5 kilogram hydrogens in carbon fiber reinforced high pressure tank. So normally we design the tank by the carbon fiber reinforced with high pressure, which weight there is 87.5 kilogram. Vehicle can refuel about the 3 minutes. It will take only 3 minutes to refuel the hydrogen Fuel cells take output power that is a 114 kilowatt maximum. And energy system features is NIMH battery. Okay, so this type of battery they use in the Toyota Mirai. Okay, so this is the practical example in the 2016. I will add the latest model, 2025 model in the PPT, correct? So once I will share the PPT, so I will update the latest model of the hydrogen vehicle. Okay, so this one is the around 9-year back. Now, last topic, hydrogen storage system. Not the last topic, second last topic, but it will not take too much time because this is the theoretical. Hydrogen storage system for the fuel cell. Hydrogen storage system for the fuel cell and e-mobility application. So, how we can store the hydrogen and which type of medium we can store. So, hydrogen can store in the three main form. So, first medium, that is a compressed natural gas, we can say CNG. Second, and liquid hydrogen storage, and third one is a solid state hydrogen storage. So we can store the hydrogen in these three medium. First one is a compressed gas store, that is a CNG. Normally in India, vehicle is available for CNG base. Second one is a liquid hydrogen storage, and third one is a solid state hydrogen. So every medium has some advantage and some disadvantage. So compressed gas storage, hydrogen is stored as a gas at high pressure. So typically pressure is too much high. There is a 350 to 700 bar. It is a too much high pressure. Storage medium, cylindrical tank made from the carbon fiber, composite or metal alloy. So tank, most important part because we have to store safe, correct? Otherwise maybe the leakage is happen, then maybe the hazards happen. Advantages for the CNG gas, mature technology because CNG is very old technology, fast refueling and high reliability. Okay, but challenges require strong and heavy tank. So suppose you want to store the hydrogen, so it is required the strong and heavy tank. Lower energy density compared to the liquid and solid storage. So suppose density is less, then you will get the less power. Okay, so compared to the liquid and solid, you will get the less energy. Second one, liquid hydrogen storage. Hydrogen is cooled to Psychonich temperature. There is a minus 253 centigrade and store as a liquid. So we can store as a liquid form. Storage medium, Psychonich insulated tank. So particular special insulated tank is available. Advantages, higher energy density, again gaseous hydrogen. So that is the most important part, and compact storage possible. Okay, but challenges, high energy required for the life fraction and boil off losses over time, and complex and expensive insulation system because it is a liquid form. So obvious there is a chemical process. So there is a complex and expensive insulation system. So we have to provide the proper insulation. So these are the challenges for the liquid hydrogen storage system. Last one, solid state hydrogen storage. Hydrogen is absorbed onto solid material. So we can use the solid material, and that hydrogen is absorbed in the solid material. Type is metal hybrid, metal hybrids, chemical hybrids, and nanoporous materials. So this type of material we can use to store the hydrogen, and that is a solid form. So advantage is high volumetric density. So you will get the high volumetric density, potentially safer, lower pressure and low temperature. So these are the advantages for the solid state. But challenges, slow absorption and deabsorption rate, high cost of material because this cost is too much for this material, temperature sensitive. So suppose 1 degree centigrade temperature will change, so we will get like less efficiency depend on the material. Okay, so these are the three form of hydrogen we can store and we can utilize for the fuel cell. Comparison, this is the comparison for the compressed natural gas, heavy tank, lower energy density, liquid form evaporation losses and insulation cost, and solid state storage, that is a costly material and slow kinetic energy, correct? So these are the some advantages as well as the disadvantages, but normally we can use that is a natural gas, so there is a like CNG type. Okay, key challenges in the hydrogen storage: balancing weight versus the storage capacity, because we have to balance the weight of the hydrogen as well as the storage capacity. Second one, reducing cost of the storage tank as well as the material, improving the safety and reliability because hydrogen is a very dangerous, scaling up for the widespread vehicle use. So these are the key challenges. In the beginning of the lecture, I also told you in the hydrogen major two challenges. First one is a safety issue and second one is a your storage, correct? How we can store the hydrogen. Now last topic of this unit, there is a supercapacitor. So supercapacitor is nothing but your normal capacitor, but we can use the advanced level technology, then we can make the supercapacitor. Otherwise we can say the ultra capacitor. Maybe you heard about the ultra capacitor as well as the supercapacitor. It is an electric double layer capacitor, so it is the same like the capacitor, but it is an electric double layer capacitor or energy store the device that bridge the gap between the conventional capacitor and rechargeable battery. Okay, so this supercapacitor is not like the simple battery. It is a combination of the both, that is a conventional conventional capacitor and rechargeable batteries. They are widely explored for the electric vehicles, hybrid electric vehicles, and public transportation system due to their unique performance characteristic. So what are the characteristic? So key characteristic, high power density. So ideally for regenerative braking and acceleration. So there is a high power density, fast charging, long life cycle, wide temperature range, and low energy density. Not suitable for the long duration of the energy store. So suppose you want to use the quick energy store, then we can use the supercapacitors. Okay. So these are the key characteristics of the supercapacitor. Why use the supercapacitor for the transportation? In the transportation, quick burst of the power, because we have a huge amount of the energy, correct? So quick we can get the power, high efficiency energy recovery, rapidly charge and discharge, frequent cycle with minimum degradation. In the battery, during the time interval, it will degrade. But in the supercapacitor or the ultra capacitor, it is a minimum. So that's why people are going to use supercapacitor in the electric vehicles also in the near future. So nowadays that is on the research topic, but in the near future, maybe the people will replace battery with the supercapacitors.
Sir,
Yes.
what are the dielectrics inside the supercapacitors?
Exactly. As of now, I don't know, but many materials are available in the dielectric for the supercapacitor. As of now, I don't remember dielectric. As of now, I don't have any answer for the dielectric. What type of dielectric we can use? But I will tell you in the next class. What type of dielectric material we can use in the supercapacitor, correct? So I will inform, otherwise I will discuss the pictorial view of the supercapacitor, correct, in the next class. Is it okay for you?
Okay.
Okay. So comparison with the battery and the supercapacitor. So energy density for the supercapacitor there is a low 5 to 10 watt hour per kilogram, but in battery there is a high 100 to 250 watt per kilogram. But power density there is a very high 10,000 watt per kilogram, but in the battery there is a moderate. Life cycle more than 1 million cycle, but in the battery there is a 500 to 2000 cycle. Charging time second to minutes, but in the battery there is a more hours. Temperature stability in the supercapacitor excellent, but battery there is a moderate. Maintenance low, and in the battery there is a moderate. Yes, supercapacitor is one of the research topics, so maybe you can consider for your project. Yeah, maybe you can consider for your thesis part. So what you can do the simulation for the battery as well as the supercapacitor, and you can connect the this battery and supercapacitor for the same specification of the vehicles, correct? And then you can characterize. Okay, so this is the one topic for your project as well as the your thesis part. So challenges for the supercapacitor: low energy storage capacity limit. There is a long range use. Cost per watt hour is higher than the batteries, and require the integration with the other storage system for the full EV use, because quickly we can discharge the quickly supercapacitor discharge. Okay, so for the integration it is required to other energy storage. So maybe we can club with the battery and the supercapacitor. So these are the challenges for the supercapacitor. Future trends. So yes, integration is required. So that's why it's a hybrid energy storage system, combining the supercapacitor and battery. Graphene based supercapacitor. So maybe that question was insulation, correct? You asked the insulation, correct? So insulation, yeah. What type of question you asked?
What are the dielectrics used in the supercapacitor?
Dielectric, correct? Yeah. So graphene based supercapacitor for the higher energy density. So normally we use the graphite for the higher energy density. Solid state and hybrid supercapacitor for the enhanced performance. So these are the future trends to design the supercapacitor for the transportation. So key point from the today's class: size of the fuel cell plant, balance of the plant and hydrogen storage system, and last one there is a supercapacitor for the transportation system. So from the next class we will start the fourth unit, and there is a energy management, otherwise we can say the power management. So key function block of the EV power management system and types of the power management strategy. So in the next class I will start with the question answer session, and then I will start the next unit, that is a fourth unit. Any confusion, any query? So I will note down your question. So dielectric medium, correct? Any other query, other question from the today's class? So one question was dielectric medium. Any other question from the today's class? Yes, student. Any other question for the today's class? Okay, no question. Then we will meet in the next class, maybe on the Thursday, yeah, Friday, because tomorrow I got the request from the students, so Wednesday is not possible. So I will take next class maybe on the Thursday, yeah, Friday, correct? So thank you so much for your attention and attending the today's class. So we will meet in the next
Thank you,
class.
sir.
Is there any confusion, any query? Okay, so thank you so much. Have a good day.
Thank you.